Good morning, everybody. I'm Ahmed Awsaf. Today, I will be presenting a brief introduction to the BERT architecture. We will be talking about its architecture, its usage, its application, and its limitations. BERT, for short, is a bidirectional encoder representation from transformers. This is a deep learning model designed by Google, and it uses concepts of the transformer architecture. It is highly efficient when reading text in both directions, which makes it a very good candidate for language translation. If we look at language translation, we need to first look at how it was translated and why BERT was made. Okay, before we dive into the BERT architecture, we must first see where how the language translation was done before the BERT architecture. Before the BERT architecture, transformers were used, and before transformers, LSTM architecture were used. This LSTM architecture was very slow and inefficient, as it took words one word at a time sequentially, and it outputted the words one word at a time also sequentially. It was slow to train, and the fact that it was just unidirectional, which means it went in one direction when it passed the words, made it that maybe the true meaning of the sentence was lost. To solve this, people modified this architecture or this setup of encoders to a bi-directional option, where not only was the sentence passed on to the LSTM one word at a time from start to end, but also it was passed on from the end to the start, so in the opposite direction. But yet again, this was done sequentially, which made it highly inefficient, and the meaning of sentences per context in this case were lost. Okay, now let's look at the transformer architecture. The transformer architecture is a much faster architecture than the LSTM architecture in case of translating. It does faster translation as the inputs are taken in a simultaneous order, and it is also bidirectional as it is also taken simultaneously. So what this does is that it helps build a better context when sentences are inputted, and more meaning is being extracted by transformers rather than the LSTMs. Okay, so how this works is that the inputs are taken, or the sentence is taken, and the encoder part of the architecture, which is this part, it creates an embedding. This embedding comes from this part and is being fed to the decoder part, which is this part, and this decoder part basically produces an output from the embedding. This embedding part has similar values for similar words. So the encoder and decoder, they vary when it comes to functionality. The encoder takes in what is the grammar and the context of the sentences, while the decoder just translates the English to another language, so one language to another, and uses the context from the encoder to determine the order and the proper words that has to be outputted. Okay, so transformer architecture seems really good when it comes to translating from one language to another, but it has its own caveats. Although the encoder part, it finds grammar and context of the sentences, the decoder part just translates according to the embedded data sent by the encoder. Both of these parts have their own role when it comes to translating. But both of them, they find another hidden part, which is what is language. So computer scientists or coders around the world, they found out that One of the key aspects of a sentence when it comes to translating is what is language, understanding language. Both encoder and decoder in some parts understand language, but not completely. Therefore, we have two other models made from these encoders and decoders, which are called, or which we know as BERT and GPT. Stacking up decoders make GPT, and stacking up encoders make the model that we know as BERT. Okay, so now that we have seen what BERT is and how it is made, we have to go back to the definition of BERT. So BERT is short for bidirectional encoder representation of transformers. So after seeing all of this, the definition or the whole abbreviation makes more sense. It is a bidirectional encoder representation, which means that it is made from stacking up multiple encoders from the architecture of transformers to be built. And the key word here for, or the reason why this is done, is to understand better language. But why do we need better language? Translation is already done pretty well by the transformers. Why do we need BERT? Or why do we need language? One thing that is poorly done by transformers, although can be done by transformers, but is poorly done, is utilizing language. So now that we have the architecture of BERT to understand language better, we can change BERT and modify BERT to not only translate language, but also use language to generate answers. So some of the usage that BERT has that transformers are weak in, as they do not understand language as much as BERT or GPT, is the usage of answering questions. So if you ask BERT a question, it can generate an answer for you. If you give BERT a certain paragraph or a lot of paragraphs, it can summarize it into text. And as it understands language, it also can understand sentiments, like uh, like things people say when they are sad, or maybe in some cases forms of sarcasm. Okay, now let us look further into the BERT architecture. So as you can see in this diagram, uh, the BERT architecture has a stack of encoders that we have seen from the transformers. So basically it starts with an Elmo LSTM, which basically tokenizes the input so that the encoder can better understand the words. Then it goes through a series or layers of encoders and then fed into feed-forward neural network, which is then normalized and softmaxed to get our desired output. If we look further into the encoder, we will see that the encoder also has some features that are crucial to understanding BERT. One crucial feature that the encoder has is its multi-head attention mechanism. This is crucial when understanding how BERT creates relation between the words. So let's look further into multi-head attention mechanism. To understand multi-head attention mechanism, we need to first see self-attention mechanism, which is a key feature in the transformer architecture. What this does is it creates proper relations between words or sequence of words, and it does such simultaneously. So all the words have a value which show relations to other words. So for example, if we look at a sentence, suppose right here, the quick brown frog jumps over the lazy dog. Here, first the quick word is taken, and then it is related to other words, and a value is created with the other words. If we look at the formula, The formula says QKV is equal to softmax QKT divided by root over dk by v. This formula has the Q vector, which is the query vector. The query vector basically represents the word that we're focusing on. So suppose in the previous example, when we said quick, quick is the word or the query in the formula. And the key or K is the key vector, and this key vector basically contains information about the other words that does not include quick. So in the previous example, quick was a keyword and the rest of the words are the k vector. Dk is the dimension of the key vector so that it gets scaled to the q vector, and the v is a value which helps the final representation based on the attention score. The whole thing is then softmax to normalize it between 0 and 1. Now let us look at the multi-head attention mechanism. Okay, so this mechanism basically uses multiple self-attention mechanism and concatenates it to get our final value. So as this diagram shows, there are multiple self-attention mechanisms and they are all done simultaneously, and then they are concatenated to find the final value. Each of these self-attention mechanisms are being called head, and the multi-head mechanism basically stores the value of the concatenated uh, head values basically. This helps the model get a better perspective of the language that we are putting into the model. It provides a richer representation of the data, and it helps the model learn better relationships between words and processes. Now let us look at the details of how the model is trained to do certain tasks. So one part of the training process is called the masked language modeling. What this does is basically takes a sentence. Suppose in this case, how are you doing? So this should be you. This should be you. So this word is masked, and many other words are masked. So 15% of the words are masked, and they are passed through the BERT masked language model, which then predicts the outcome or predicts the word that is highly likely to be there. So what this does is it predicts the word and basically trains itself to complete certain words or certain sentences. Sort of like the fill in the blanks that we used to do during our school years. The formula or the mathematical expression that MLM uses creates a value between 0 to 1, which basically holds how relative the word is to that sentence. Another part of the training is the next sentence prediction. Both the MLM and NSP, they work together. What this does is basically finds uh, finds out if the next sentence is relative. So basically, during the training process, we create a paragraph of actual sentences and then add a few sentences that are completely random. So, for example, if we were talking about sports in one sentence and in the exact next sentence, there is no sports, there is just politics. So they are unrelated. So we get a value of 0 or 1, signifying if they are related or not. So this formula basically helps us find that value. As you can see here, the tokens are passed and they are working simultaneously. MLM and NSP are working simultaneously. NSP is telling us if the next sentence is relative, and the MLM basically fills in all the blanks and all the spots that we have. Okay, now I will talk about the limitations of BERT. One obvious limitation would be that it is highly resource expensive. I mean, if you're trying to teach a model a certain language, or like the English language itself, it obviously needs a lot of training data and a lot of pre-training. And the stack of encoders mean that it also has to be computationally heavy, which is highly expensive if you look at current standards. Another problem is its limited input size. Currently, the max input or the max token size is 5112, which is very limited. And beyond 512, the data is deleted or truncated, which may have the risk of some data being lost. The last limitation is that the model has static context. By static context, we mean that BERT is fixed to certain number of context and it does not know anything beyond it. So the context is not dynamic and but rather fixed, which means that it only knows what it already has been taught. So that is all for now. Thank you for watching my presentation. I hope you got a brief idea of the BERT architecture. Thank you.